thank you very much. Today, I'm going to talk a little bit more about the magnetic tunnel junction as an enabling device for a whole class of technologies that Kevin has just sort of very generally introduced nicely. We all know, let me see, my control is not working. Yeah, so the magnetic MRAM STT-based has seen more products being offered, and it is, standing alone chips on the order of a gigabit sort of size has been in production ever been together with global. And the industry roadmap is looking forward towards embedded memory space, which means the STT-MRAM is going to be integrated to the back end of logic circuits directly, as opposed to be standing alone. That brings the memory much closer to operations. Seems to be the trend of things when we're dealing with very large sets of data in AI and machine learning and such. So the goal, sort of intermediate state goal, is to have them certainly replacing flash, embedded flash, and most likely will be taking the slower end of the SRAM, the cache memories. For example, there are some efforts on Intel side as well, which may eventually lead to chips with MRAMs, commercial processors with MRAMs in them. So these are the sort of landscape of the industry. And of course, magnetic tunnel junction, as we all know, is the enabling device that made a lot of these advances possible. Magnetic tunnel junction is no stranger to us. Actually, as a sensor, it played a very significant role in computing. That's still being very widely used in hard drive readout. And it's also used for all kinds of mechanical encodings and whatnot. I'm not going to talk too much about that. And as I just mentioned, the emergent solid-state memories, STT-MRAMs, are largely based on magnetic tunnel junction, both for reading the state and for writing the state. And further down the road in the horizon, there are new possibilities for applications, especially now that we have an infrastructure in place where the magnetic tunnel junction is integratable to very large scale CMOS circuits. One particular example I hope to find some time to get into is the stochastic bit stream generator, which means you have a very energy efficient, very compact entropy source for computing for p bits or Monte Carlo or what have you. So back to the basics. The tunnel junction physics, of course, as we all know, is based on the spin polarized subband density of state, having a up and down spin state contrast, both in terms of the tunnel matrix and also the matching of the wave functions. In fact, that sort of enabled a lot of these device characteristics. Two sort of significant ways of looking at it. One is from summing up the tunnel current, particle current with its charge, which gives you the charge conductance description, or in other words, tunnel magnetoresistance. The other is to sum up the spin component of the particle transport, which gives you the spin current during tunnel transport, which is, of course, the ST spin transfer torque that drives the nanomagnetic dynamics. So the charge piece is sort of coming on to computing scene earlier. And as I said, it's already very widely used in sensors for hard drive readout and encoding and whatnot. It's based essentially on summing up all the particle currents with electron charge attached to it. And that's sort of tried and true, whereas application is already fairly widespread and to some degree reasonably mature technology. The spin piece, on the other hand, sort of both the physics and the technology are still very much evolving. The physics is understood, of course, also for quite a while, dating back to the 80s, where I'm showing you here is a very characteristic sort of pinch the middle bistable state tunnel junction IB characteristic. You have the parallel and anti-parallel state. At low voltage, you can read those states out. At higher voltage, the spin current will impart some angular momentum to the ferromagnet in the free layer or the reference layer both, and resulting in a magnetic switch. So you can switch between these two states. It's that charged current regulated spin current that gives you the ability to embed this kind of device in a charge circuit. And that's what we use for memory, where in still almost, I would say, all of the current generation technologies are based on one transistor, one tunnel junction memory cell, where the transistor does the address selection and couples that particular tunnel junction to external circuits, where it is either read out with a relatively low voltage or written with a higher voltage driver. So that's the technology that we are putting this tunnel junction device into. What are the constraints and boundary conditions? The technology, of course, is the gigantic train of CMOS for computation, and that is the Moore's law and beyond, being scaling for many decades and has a huge set of economy going behind it. So it's sort of, for commercial application, dictates the device parameters we have to fit into. Here is a roadmap of the semiconductor crowd from about maybe a year ago, predicting for over the next decade with various improvements on the transistor technology, where the very basic transistor on-state current supporting capability is, very crudely speaking, and also what is the source drain and the supply voltage is. So this is kind of like the square hole the pigeon has to fit into for magnetic tunnel junctions. Long story short is, most likely a operating tunnel junction would have to have its functional switching current below 100 microamps for whatever application you envision. So then we can flip the coin a little bit from physics side. How much current is necessary for switching a nanomagnetic memory bit? This is a simple question, but it turns out that the answer is rather nuanced. And on a very fundamental level, there are two intertwined factors from somewhat different origin that contributes to the amount of switching current one needs. One is the question of how much spin current one needs to switch a nanomagnetic bit. That relates to magnetodynamics, either in the simplest case, macro spin, of course, and in real world, nothing's macro spin, and at finite temperature. The other factor, of course, is how much charge current would one need to deliver such a spin current for switching. And that has to do with details of transport physics, either in the tunnel junction case, spin filtering, basically, or in what Kevin has described earlier, spin orbit torque and other mechanisms. You tap into the nature of orbital transport, where a lot of angular momentum is changing hand. How to harness these different mechanisms is the subject of day for both scientific understanding and technology development, materials science optimizations. So just take a step back to ask, what is the amount of spin current required to switch a nanomagnet bit? It's, of course, determined by the dynamics, which is pioneered by John Slonimsky's understanding in the 80s. If we go back a step to look at the sort of classical picture of dipole moment, magnetic moment in a magnetic field, of course, the leading torque on the dipole moment is the magnetic field that gives you the precession frequency, which we all measure by fMR, tens of gigahertz easily. So that's the leading torque, but this is an energy conserving torque. It only keeps the moment on a constant energy orbit. Also important is dissipation. So if not supported by any external energy source, this is going to decay into energy minimal state. And the decay process is phenomenologically described by damping, which is easily a factor of 100 or 1,000 times smaller in terms of magnitude compared to the field torque. So this is a small torque. The difference is this piece is energy conserving, the field part, whereas the damping piece is energy non-conserving. That's what made a world of difference. Now, with spin current, what you have is essentially a third term. If we assume in the simple case where the spin current is collinear with that of the axis of easy axis of the anisotropy or magnetic field, then this spin current term turns out to be exactly of the same form as that of the damping, in that their vector axes line up. So basically, you can use the spin current as a knob to either augment the damping or to counter the damping, thereby generating the so-called anti-damping switch. Instead of climbing successively lower energy orbits, the spin transfer torque allows you to climb higher energy orbits, eventually overcome the equator and go from North Pole to South Pole, accomplish a precessional switch. And that's basically the mechanism for spin transfer torque induced switching. And that's still all the mechanism fundamentally what one uses for today's STT-MRAM. Of course, for memory, you need a bistable state to start with to distinguish the state 0 from state 1. And that has to be also stable over time. And these devices usually operate at ambient temperature for commercial applications. And for that, it sets the energy scale of the energy barrier. If you have a very simple sort of uniaxial energy landscape, ask anybody magnetic recording, they'll tell you that energy scale is on the order of 40 to 60 KT of ambient. So given that, you basically know the strength of the magnetic field or the anisotropy field that one needs to apply on the nanomagnet. And that immediately gives you the threshold for anti-damping switching, which is proportional to the damping coefficient and proportional to the magnetic field. But effectively, that torque is about a factor of 100 or 1,000 lower than that of the magnetic field alone. That's the efficiency of using anti-damping as a mechanism for switching. And that's a step in the direction where the technology wants to see, basically lower switching current. But that's only a threshold current sets the scale for switching. It doesn't mean it satisfies all the technology needs. For technology applications, you need to switch it fast and you need to switch it reliably. Both require more spin current. How much more? In the 0 temperature, this is well understood. That is, the speed of switching is proportional to that of the spin current supplied above the threshold, and it's also inversely related to the initial state of the cone angle. The further away from the equilibrium, lowest the energy state cone angle, the faster it switches. So large cone angle, initial state, quick switch, and low cone angle, slow switch. But in reality, of course, all these devices operate at finite temperature. And that means when your right pulse hits the nanomagnet, you have chance of hitting any of these initial angles thermally distributed on a Boltzmann curve. So you wind up with having a distribution of likely switching speed, but not a unique switching speed. You switch the variable on that, which basically means there's a probability of switching for any given amount of spin current and pulse width. The more faster you want it to switch, the more spin current you need. And the more reliable you want it to switch because of this probabilistic distribution, the more spin current you need. Reversal is therefore fundamentally a probabilistic process. One needs to do the statistical physics right. And in the macro spin world, this is done a while ago. And the basic story is, I'm not going to bore you with formula and such, but the qualitative take-home message is there is a log linear dependence of the switching residual error. We're talking about small errors, 10 to the minus 6, 10 to the minus 9, that has a log linear dependence on the amount of spin current that's necessary to switch it from the macro spin modeling prediction at finite temperature. And that's determined by this thermalized initial cone angle. And the other aspect of that is the shorter the right pulse of spin current, the larger spin current needs to be, and the shallower that error slope is. So long story short, again, higher speed, lower error rate means more spin torque required and more spin current required. And that's the reality that we are dealing with for developing products in magnetic tunnel junction and STT-based memory. But in the experimental field, repeatedly over the last decade by many groups, what we observe is actually the situation in terms of switching error slopes is somewhat better than what the simple macro spin model was predicting. Here I give you an example of a cobalt ion boron MgO type of tunnel junction of about 30 nanometers in size and with the energy barrier of about 50 KT, give or take, at 5 nanoseconds switching. The highlighted data point are these black circles. And if you take the same tunnel junctions materials parameter, which we know fairly well, and plug it into a macro spin prediction model, you wind up with these yellow dashed lines. So the difference is that the real samples would have a somewhat higher threshold current to get the anti-damping started. But once you started to switch, the error decrease upon the increase of spin torque is faster. So you achieve a lower error floor at lower voltage better than the macro spin model would predict. Now, that's very good news for technology. And indeed, that's what enabled a lot of the recent progress in integrating perpendicular STT MTJs into backend CMOS to fit into the CMOS current budget. It's that in practice, it is better kind of narrative that actually is enabling these products. Very good news for technology, but it will be very nice to know scientifically why. And it turns out, long story short, the fundamental reason is because we are not dealing with macro spins in 30 nanometer devices. And what the consequence of that is the magnetic exchange length or the coherent volume for dynamics in such structures is smaller than the full diameter of the free layer. As a consequence, the thermal fluctuation makes it such that it's highly unlikely that your entire free layer is going to reside in the low energy state when the right pulse hits. That's where the stagnation and this long log linear error slope originates. Instead, in a sub-volume situation, there are different regions of the tunnel junctions free layer that's fluctuating at different rate and different position. So there's always something present when your spin current arrives to initiate the spin transfer induced switch. And that enables a net smaller magnetic volume being involved in the initial dynamics for spin torque switching and contributing to this slope increase or the efficiency increase for faster switching. So key to better than macro spin switch is really avoiding the global zero spin torque states of thermal occupation, and a non-micro spin finite exchange length accomplishes that. There's a lot of materials optimization and even physical anisotropy versus exchange length versus everything else that goes into these device refinement. But the net result is you can reduce the amount of spin current required for switching such a sort of finite size tunnel junctions. As an example, for technology demonstration, 5 or 6 years ago, we published this result of realistic magnetic tunnel junctions switching down to error floors of 10 to minus 9 at 10 nanosecond. This is an existence proof. It can be done. Then many years of very intensive technology and materials optimization followed. And at 2020, 5 or 6 years later, we do arrive at magnetic tunnel junctions with not a single junction performance, but a full 4 kilobit array with very consistent switching slopes and with reasonably tight distribution for switching thresholds. So progress are being made in sort of, in this sense, through a lot of materials engineering and optimization, with the fundamental physics understood, but the quantitatives of that applying to detailed systems. There's still a lot of work to do and a lot of catch up to understand what we're actually looking at. Okay, that's the question I just answered about the role of magnetodynamics in how much spin current it needs to switch. The other side of the coin, of course, is how much charge current one needs to supply to give you that kind of spin current. And that is related to transport physics in tunnel junctions. That is well known. For a symmetric magnetic tunnel junction, for example, the tunnel spin current to tunnel charge current ratio can be written very simply related to magnetoresistance in this explicit form, which maxes out asymptotically at about 0.5. It's 0.5 only because the spin torque is shared between the free and reference layer, right? So each electron gives you half a Bohr magneton to the free layer in tunneling. That's the theoretical limit. And this asymptotic form is not very sensitive to MR once you're exceeding a couple 100%. So we're practically very close to theoretical limit in terms of filtering. Now, what other tricks one could do to increase the charge to spin conversion ratio? One thing is, of course, one tunnel barrier gives you this much conversion. Maybe we can try 2. And that will at least increase the conversion efficiency by a factor of 2. Theoretically, it could be quite a bit higher, as Daniel Woolridge's paper theoretically explored. But in real life, of course, they're finite temperature and their dynamics. You'll be pretty happy if you get a factor of 2 improvement. The damaging aspect of this approach is the optimization condition for maximizing spin transfer torque is opposite to what it is for tunnel magnetoresistance. You want to maximize tunnel, you want the two spin current to add, the magnetoresistance will subtract. And that's bad news. To deal with that, we have an approach developed to essentially intentionally remove the spin polarization on one side of the free layer. So now on the other side, the free layer, it's still fully ferromagnetic against ferromagnetic tunneling that provides the large tunnel magnetoresistance. On the other side, the free layer side has essentially eliminated spin density difference at the tunnel interface. Therefore, it does not contribute to additional magnetoresistance. And you can reduce that tunnel junctions interface to much lower resistance. In combination, that mitigates the resistance damage, tunnel magnetoresistance damage. But if that spacer is designed right, it can still absorb the tunnel spin polarized current from the second interface and absorbing the needed spin current augmentation, which give you about a factor of 2x improvement, which we demonstrated this past IEDM with integrated tunnel junctions here at low RA. You can see there's about a factor of 2 improvement in the switching current reduction. So this is kind of device physics development and the materials optimization that we are currently engaged in. The work is ongoing. It's a long journey from John's original idea in the 80s of a nanomagnet being driven by spin polarized current to the demonstration of these tunnel junctions that indeed can be switched by spin current to our first generation standalone products already incorporated in IBM systems and future developments on the way and ongoing. So this is the current status. And I would also like to sort of describe a little bit about the concepts on the horizon. There's many exploratory efforts, as Kevin also mentioned towards the end of his talk. Most of these each would deserve a talk of their own. So I'm not going to cover much of these different aspects. The one thing I would like to spend a few minutes on would be to use the magnetic tunnel junction as a controllable stochastic number generator for perhaps probabilistic computing or many other applications where you need a cheap and compact entropy source. So the idea basically is we tried very hard here to make a memory bit, but the flip side of that is if my magnetic tunnel junction is super paramagnetic, it provides you with a very small footprint, very low power consumption, so the physical process-driven entropy stream. If you can read that out with a read circuit not so different from that of a memory, you got a cheap entropy source in computing circuit right there with integration technologies already in place, more or less. So if I do a very quick back of envelope estimate, I would say that if you can read these entropy signals out at 2 nanosecond intervals, it will cost you only about 60 femtojoules per bit. You can sort of ask the technologist how much they're paying for stochastic bits today is orders of magnitude better. So if you have such a stochastic random bit embedded in CMOS circuitry, then it is possible to implement a whole class of different computing systems. One such example is being explored at Purdue University by Professor Supriyodada and Karen now is in Santa Barbara. So there are many other possible system level discussions ongoing using this type of bit streams. And it's very consistent with the workload of AI and machine learning, actually. So there are a lot of advantages to explore there. So can magnetic tunnel junction do that? The question is, can you pull a very fast and stochastic bit stream out of it? And it's truly random. Early work from the NIST group demonstrated that there are certainly nanosecond or even sub-nanosecond dynamics you could invoke by spin torque biased spin valves. I had some discussion going with the Purdue University group earlier to say that if we have a magnetic tunnel junction that is super paramagnetic in that it has no preferred uniaxial axis or not strong, but is confined in very strong easy plane anisotropy, then it is feasible to, at least in macro spin limit and with numerical modeling, to achieve at finite temperature very narrow autocorrelation times. In this case, with some fairly prototypical kind of materials parameters, you can get down to, a fraction of a nanosecond very easily. And this is usually a challenge if you think about purely uniaxial situation, because there are competing interactions between the thermal activation and the attempt frequency. In the end, you max out at like speed-wise at about 10 nanosecond or 20 for typical materials numbers. You need to have these new mechanisms to let it go faster. So this was the theoretical exploration that we did with the Purdue University group numerically. That seems to be a feasible path forward. And indeed, last year, we put some of these magnetic tunnel junctions onto our silicon chips and tested them in high bandwidth measurement experiment. And indeed, we have demonstrated with typical easy plane cobalt-iron-boron type of tunnel magnetic tunnel junctions, we can observe at least 5 nanoseconds of correlation time in stochastic number generation or in analog sort of noise output. This 5 nanosecond number is completely limited by measurement capability, because for a very small tunnel junction and you want to be CMOS compatible in impedance, there's huge amount of attenuation one has to deal with, because all the broad high bandwidth measurement is 50 ohm based, and they're the Johnson noises and amp noises one has to deal with. But when the tunnel junctions behavior poke out of the noise floor, you can see it loud and clear that it is doing the random fluctuations on a time scale, and it correlates to the material parameters as we understand. We have to control the easy plane anisotropy and everything else so that it's not too strong, the speed is too fast that our circuit would not be able to measure. So this is not the limit by any means, but rather a sort of indication of viability in terms of the basic physics. So here is basically my summary of where we are with magnetic tunnel junction. It is an enabling component for several future computing concepts, from bringing memory to logic, to neuromorphic accelerators, to non-volatile radiation hard solid state memories, perhaps for more sort of captive markets. CMOS backend integration is in place with commercial products coming out, and also foundries are offering these as possible technologies for integration with customer designs. And continued progress are being made on device physics understanding and performance improvement, both in terms of charge to spin current conversion and the switching dynamics. Active research is, of course, currently underway for faster switching, more reliable switching, for SRAM replacement, for integration with spin orbital-based memory cells, which, as you heard from Kevin, potentially can offer better charge to spin conversion rate. And also, I just described to you that there are some thinkings ongoing that maybe the other extreme of the magnetic tunnel junction, instead of memory, but in the super paramagnetic limit, could provide some attractive device applications as well, giving you a very compact and low power random number generator for integration with large scale digital applications. So with that, I thank you for your attention.